Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 3450, Mission to Mars, Lecture 4, Orbits, Part 1. So this is going to be a fairly long lecture, and I'm going to break it into 4 parts. And in this part of the lecture, we're going to talk about basic orbits. We'll talk about the early history of determining orbits, primarily of the planets, and we'll talk about Kepler's laws of planetary motion. In our second lecture, we'll talk about how it is that we define what an orbit looks like, its shape and its orientation in space, and then from there we'll talk about the different types of orbits that are used, especially when we talk about satellites in orbit around the Earth. In our third part, we'll talk about changing orbits, why orbits change over time, and then things that we need to do when we want a satellite to move from one orbit to another. And then in the very last part, we will talk about launch windows and orbital rendezvous. So let's talk about the history of orbits. Of course, long ago, people didn't think about satellites orbiting the Earth. When they talked about orbits, they were thinking about planets orbiting the sun, planets moving through the night sky. For example, here's the path of Mars from May 2020 to March 2021. And if we look at what Mars does over that time period, here it is down here in May of 2020. You can see sort of every couple weeks as it moves through the sky. But then in September of 2020, Mars did something odd. It stopped moving forward and it started moving backwards for a while. And then in November, it stopped moving backwards and it started moving forward again. And right now, in February of 2021, it's moving forward through the sky. Now, the Greeks needed to come up with an explanation for this. This, by the way, is called retrograde motion. Retrograde because it's against the grade. It's opposite the normal direction. Today, we know that Mars is, of course, orbiting the sun. The ancient Greeks didn't believe that. They believed that the Earth was the center and Mars was orbiting the Earth. So we'll see the consequences of that in a minute. We know today that Mars, as it orbits the sun, is moving through the sky like this, and the reason that it stops and moves backwards for a while and starts moving forward again is because we pass Mars in our orbit. We are closer to the sun than Mars is. We're going faster than Mars, and as we pass Mars, it looks to us like Mars is going backwards, even though it's going forward. All the outer planets do this. This is the path of Jupiter from November 2018 to March 2022. And you can see that every year Jupiter spends a time going backwards and then stopping and going forwards again, and then stopping and going backwards and going forward again, and then stopping, going backwards and going forward again. And you'll notice based on the dates here, April, May, June, that Jupiter does this every year. And as I said, we see that because we are traveling faster than Jupiter is, so it looks to us like Jupiter is moving backwards. But the Greeks did not believe that the Earth was orbiting the sun. The Greeks believed the Earth was at the center. And a variety of Greek scientists, Hipparchus and Ptolemy, amongst others, developed an idea with the Earth at the center of the universe, the planets orbiting the Earth on a circle called the deferent, and then the planet itself orbiting the deferent on a small circle called the epicycle. And what would happen is this epicycle is carried around in a circle around the deferent, but the planet is orbiting on the epicycle. And when the planet is on the inside of the epicycle here, it looks like to people on Earth that the planet is moving backwards. Because even though this whole circle is moving forward, when the planet is on the inside of the circle, it can look like it's going backwards. So just out of curiosity, go out to the lecture exercise and answer this question then. When the planet is undergoing retrograde motion, when it's on the inside of that circle and moving backwards, how will the planet appear in the sky? Will it be the same size and brightness as average? Will it be larger and brighter than average? Or will it be smaller and dimmer than average? So go ahead and think about when the planet is going through retrograde motion like this, whether it will be the same size and brightness as average, larger and brighter than average, or smaller and dimmer than average. So what did you get on that one? When the planet is undergoing this retrograde motion, when it appears to be moving backwards in the sky, it is closer to the Earth than it is at any other time on its epicycle. And because it is closer to the Earth here, it will appear both bigger and brighter. And so it was interesting that this model that Ptolemy produced, and Ptolemy refined this model and finished refining it around 150 CE. Hipparchus first developed the idea of epicycles about 150 BCE, and Ptolemy solidified it about 150 CE. And Ptolemy did such a good job at describing the motion of the planets through the sky that his model survives for over 1,300 years. It is the primary model of how our solar system works. Now, to get into the details a little bit, we won't get into too much details. In order for Ptolemy to be able to accurately model the positions of the planets in the sky, because after all, that's what he was trying to do, he would see the planets moving through the sky and wanted to understand what was causing their motion so that he could predict where they would be in the future. He had to do a few things. He had to take the Earth and move it off center. So the Earth was no longer at the center of the deferent, but it was off on one side. And then this epicycle, as it orbited around the deferent here, orbited at a constant speed, not around the center of the circle, but at a constant speed around this other point that he called the equant point. He had to do all of these because, of course, his model was incorrect by placing the Earth at the center of the solar system. But nonetheless, he did such a good job at predicting the motions of the planets that his model of the solar system survives for 1,300 years. We don't get a major overhaul of our model of the solar system until Nicholas Copernicus comes about. Now, Nicholas Copernicus was born in 1473. He dies in 1543, and he dies just as his famous manuscript is being published. His manuscript was on the revolutions of the celestial spheres. Copernicus argues that the motions of the sun and the planets through the sky could be better described by a system in which the sun was at the center and the Earth was going around the sun. So he was unhappy with Ptolemy's model because Ptolemy's model, as I said, had to make all these adjustments by putting the Earth off center and then having this other point called the equant point. And Copernicus didn't like that. He believed that everything should orbit on perfect circles, that all celestial motion was perfectly circular and that it was uniform at a constant speed. Well, that's not what we see when we see the planets moving through the sky. They're speeding up and slowing down and moving backwards. So Ptolemy came up with his ideas, which Copernicus didn't like. Copernicus proposed a separate idea. And his idea was, we assert that the center of the Earth, carrying the moon's orbit, passes in a great orbit in an annual revolution around the sun, that near the sun is the center of the universe, and any apparent motion of the sun can be better explained by the motion of the Earth. In other words, the sun is the center of the solar system. The Earth goes around the sun, the moon goes around the Earth, and the Earth carries the moon with it, and all the planets are orbiting around the sun instead. Now, this model was very much simpler than Ptolemy's model. For example, let's talk about retrograde motion. In Copernicus's case, retrograde motion comes about simply because the Earth is orbiting the sun faster. The analogy that I like to use is, imagine that you're driving on the interstate and you're driving 70 miles an hour and you pass a car that's going 60 miles an hour. Now, you know that you're both going forward. You're going 70, they're going 60. But if you think about what happens as you pass that car, as you look at the car, it looks to you like the car is going backwards. Not because the car is actually going backwards, but because you are going faster than them. And at least for a short period of time while you pass them, it looks to you like they're going backwards. That was Copernicus's explanation for the retrograde motion of the planets. The planets look like they're going backwards for a while because the Earth is passing them. And you can, if you want to sit down with this diagram, you can sit down and draw out these arrows. So when the Earth is at position A, let's pretend this is Mars. Mars is at position A. And then as the Earth goes from A to B, Mars goes from A to B. And in the night sky, it looks like Mars goes A to B. But from B to C, Mars only moves a little bit. The Earth moves a lot. And in that time, it looks to us like Mars is moving backwards. And from C to D, the same thing happens. The Earth moves a lot. Mars hardly moves at all. So it continues to look to us like Mars is moving backwards. And then from D to E, Mars is moving forwards again. Not only that, but if you think about when Earth and Mars are closest together, they are closest together when the planet is in the middle of its retrograde motion. Just like Ptolemy had discovered and people saw in the night sky, the planets are brightest and they're largest when they are closest to us. And that occurs at this time of opposition. That is, when the planet is opposite the sun in the sky, or the Earth and the planet are closest together. So Copernicus was able to explain the same things that Ptolemy was able to explain, only his model was conceptually simpler. It didn't require putting the Earth off center. It didn't require this equant. It didn't require the epicycle at all. It just put the Earth in orbit around the sun. But here's the thing. When Copernicus used his model to calculate the positions of the planets in the sky, he could do no better a job than Ptolemy could do. His model was no more accurate than Ptolemy's model. To get a more accurate description of how the planets orbit the sun, we have to wait until Johann Kepler comes around. So Kepler was born in 1571. He dies in 1630. Now, Kepler was a brilliant young mathematician, and in 1600, he was hired by the famous Danish astronomer Tycho Brahe. Brahe operated an observatory, and Brahe wanted to refine Ptolemy's model of how the planets are going around the sun. Now, Brahe was familiar with Copernicus's model that had the Earth orbiting the sun, but Brahe believed very strongly that the Earth was the center of the universe. He had observational evidence for that. He looked to see the stars moving. He felt that if the Earth was really going around the sun, he should see the stars shifting back and forth in the sky, and Brahe couldn't detect that. We know the reason today that that's true is that the stars are so incredibly far away from us that we can't detect this motion as the Earth goes around the sun with our eyes. We can detect it with big telescopes today. In fact, that's how astronomers measure the distances to stars today. As the Earth goes around the sun, the nearby stars appear to shift back and forth, not because they're moving, but because we're orbiting the sun. And we're seeing them from two different perspectives now and then 6 months later when we're over here. But Brahe tried to do that, and he couldn't detect that shifting. And again, because the stars were so far away, he would have needed a large telescope to do this. And around 1600, the telescope had not yet been invented. So Tycho Brahe is trying to refine Ptolemy's model of everything going around the Earth. And in fact, Tycho Brahe came up with his own model, which is that all of the planets are orbiting the sun, and the sun and the moon are orbiting the Earth. So the Earth is at the center of the universe, the moon is orbiting the Earth, the sun is orbiting the Earth, and then all the planets are orbiting the sun. But to refine his model, he needed to understand the precise motions of the planets. And to do that, he understood that he needed to take observations of the positions of the planets in the sky, and not just for a year or two, but for many decades. And so Tycho Brahe, spent about 20 years or so precisely measuring the positions of the planets in the sky at his Danish observatory. And remember, this is before the invention of the telescope, so he was doing all of this with the naked eye, just literally by using sighting devices, something kind of like our modern day sextant, although he had a mural quadrant and other devices, but basically devices for very accurately measuring angles in the sky with the naked eye. And he compiled this catalog of planetary positions. Now, in order to determine the model behind this, the precise movement of the planets, he needed a mathematician. And he hires this young mathematician by the name of Johann Kepler to do the calculations for him. But Brahe, he's a bit suspicious. First of all, he wants to make sure that he gets eternal credit for finally figuring out the motions of the planets. He doesn't want anyone else to get credit for this. So to make sure that Kepler doesn't make any discoveries, he gives Kepler just a little bit of data at a time. And Kepler's really frustrated by this because Kepler thinks if he can see all the data, he might be able to figure out the orbits of the planets. But by seeing just little bits at a time, he's having a hard time seeing the big picture. Brahe dies unexpectedly. And when Brahe dies, Kepler steals his notebooks that contain all of his observations of the positions of the planets. And in particular, Kepler was interested in the motions of Mars, because Kepler realized that because Mars is as close to the Earth as any of the other planets, and it's the closest of the outer planets, that if he could determine the motions of Mars, he could probably determine the motions of all the planets. So Kepler steals Brahe's notebooks, and Kepler starts analyzing these notebooks, and he uses this data to determine exactly how the planets are orbiting the sun. And he publishes this in a book called New Astronomy, or Astronomia Nova, in 1609. And in this book, he lays out 3 laws of planetary motion. And these laws of planetary motion describe how planets orbit the sun. And he got it exactly right. So for the first time in human history, people understood how the planets orbit the sun. So let's talk about Kepler's 3 laws of planetary motion. And we'll come back to each of them. So don't worry about all of them right now. We're going to start with the first law here, and we'll move on to the second and the third law. But Kepler's first law of planetary motion is that each planet moves about the sun in an orbit that is an ellipse, with the sun at one focus of the ellipse. Now, this was important because everybody before Kepler thought that all planetary motion was perfectly circular. And this can be traced in part back to Aristotle. The great Greek philosopher Aristotle believed that the motions in the heavens were perfect, and therefore they should follow the perfect geometric form of a circle. Well, Kepler showed, so Ptolemy believed that, and Copernicus believed that. And because they insisted that everything orbit on circles, they were not able to get a perfect match to the actual motions of the planets. So instead, Kepler abandoned circles and realized that planets move on ellipses. Now let's talk specifically what I mean by an ellipse. An ellipse is a specific type of geometric figure. To make an ellipse, you can take a piece of cardboard and you can drive 2 pins into the cardboard and connect the 2 pins with a piece of string. And if you put your pencil in the string and pull it taut, and then move your pencil in around the two pins, it will trace out an ellipse. And the definition of an ellipse is it's all points that are equidistant from these 2 focal points right here. That is, the sum of the distance, the sum of this distance and this distance is constant as you circle around those 2 points. What we would say today is this is the focus of one focus of the ellipse, that is the second focus of the ellipse, and then you've got the figure of the ellipse itself. So that is a diagram of what an ellipse looks like. Now, a couple definitions of terms that we're going to be using. The major axis is the widest diameter of the ellipse. So the major axis is just simply the diameter all the way across the ellipse from one side to the other side, right? So that's the major axis of the ellipse. The semi-major axis is half that distance. So it's the distance from the center of the ellipse over to the edge here. So you just take the major axis of the ellipse, divide by 2, and that gives you the semi-major axis of the ellipse. So the semi-major axis is half this distance. Now it turns out that the semi-major axis also happens to be the average distance of the planet from the sun. And the way you can see that is imagine that the sun is sitting at one focus right here, because as I mentioned here, each planet moves about the sun in an orbit that is an ellipse with the sun at one focus of the ellipse. So imagine that the sun sits at one focus of this ellipse and you've got this asteroid or comet going around the sun right here. Well, here it's closest to the sun. Here it's farthest from the sun. So what's its average distance to the sun? Well, the average distance is the closest distance plus the farthest distance divided by 2. Well, the closest distance plus the farthest distance is the major axis. And if you divide that by 2, you get the semi-major axis. The semi-major axis is the same thing as the average distance of the planet from the sun. That's probably a little bit easier to understand if you picture a circle for a second. If you picture a circle where the 2 focal points are at the center, the major axis is the distance across the circle. The semi-major axis is just the distance from the sun to the planet right there. So that's another way to picture it. But in any case, know that the semi-major axis of an ellipse is the average distance of the planet to the sun. Now, another property of ellipses are their eccentricity. The eccentricity is a measure of the roundness of the ellipse. So an eccentricity of 0 is a perfect circle, and an eccentricity near 1 is a very, very elongated ellipse. And in fact, an eccentricity of exactly 1 is a parabola, and an eccentricity greater than 1 is a hyperbola. So let's go back to looking at eccentricity. So here's the eccentricity of a couple different orbits right here. This is an eccentricity of 0. That is, it has no eccentricity at all. And another way to put that is a circle is simply a special kind of ellipse. A circle is an ellipse that has an eccentricity of 0. All circles are ellipses, but not all ellipses are circles. Here is a circle, is an ellipse with an eccentricity of 0.3. Here's what one looks like with an eccentricity of 0.5, 0.7, and 0.96. You can see the higher the eccentricity, the longer and skinnier the ellipse. All right, so go out and answer this question in the lecture exercises. What is the eccentricity of the Earth's orbit around the sun? Is it exactly 0? The Earth is in a perfectly circular orbit. Is it very small, 0.0167? Is it a moderate eccentricity like this of about 0.3? A higher eccentricity of about 0.5, or really eccentric down here, 0.9, or something else? So go out to the lecture exercises and answer this question. All right, what did you get for this one? Well, the best answer for this one is the orbit of the Earth is certainly not perfectly circular. So it's definitely not A, because Kepler taught us through his first law of planetary motion that all planets orbit on ellipses. What is surprising for most people, though, is that the Earth's orbit is very, very close to being perfectly circular. The Earth's eccentricity here is B, 0.0167. In fact, the eccentricity of the Earth's orbit is so low that if you were to draw a picture of the Earth's orbit, you could not tell that it's not a perfect circle. And as we're going to find out here in a few minutes, we're not going to go into the details of this. It's a question for Astronomy 1210. But the eccentricity of the Earth's orbit has nothing at all to do with our seasons. A very common misconception is that we have seasons on Earth because at part of the year we are closer to the sun and part of the year we are farther from the sun. And that's not true. In fact, it turns out we are closest to the sun in January of every year and farthest from the sun in July of every year. Our seasons are not due to the eccentricity of our orbit. Our seasons are due to the fact that the Earth is tilted over by 23.5 degrees as it orbits the sun. But nevertheless, here are some common eccentricities. So the eccentricity of the orbit of the space station around the Earth is 0.0005071. So that's a very small number. Again, very close to a perfectly circular orbit. The moon around the Earth is 0.05. The Earth around the sun is 0.0167. Mars around the sun is 0.09. Pluto around the sun is 0.248. So now Pluto does have a significant eccentricity, and Pluto is significantly closer to the sun when it is closest to the sun as opposed to when it's farthest from the sun. And then comets, like Comet Encke and Halley's Comet, can have very eccentric orbits. These are the eccentricities of some bodies in our inner solar system: Mercury, Venus, Earth, Mars, and Jupiter. Now, the first thing you'll notice is that most of the planetary orbits are so circular that you can't tell they're ellipses. In fact, if you look at Jupiter's orbit or Earth's orbit, it's really hard to tell that they're eccentric at all. It's a little bit easier with Mars's orbit. And the reason it's easier with Mars's orbit, if you look at the distance between Earth and Mars here, and you look at the distance between Earth and Mars over here, you can tell that it's much greater here than it is over here. In fact, the reason for that is that Mars's orbit is significantly more elliptical than our orbit around the sun. In fact, just looking at those numbers there, it's about 8 times more elliptical than our orbit around the sun. Here's an example of a really elliptical orbit, Comet Encke right here, which is on a highly elliptical orbit, or here's Halley's Comet plunging to the inner solar system and out again. Many of the comets and asteroids in our solar system are on very elliptical orbits. These blue ellipses right here show you the orbits of some of the asteroids in the asteroid belt. So let's talk about these 2 points let's look at Comet Encke here for a second, and there's a point where you're closest to the sun and a point where you're farthest from the sun. What do we call those 2 points? We call those 2 points periapsis when you're closest and apoapsis when you're farthest. So periapsis is the point on the ellipse that is closest to the body that you're orbiting. Now, in spaceflight, we typically change periapsis and we replace the word apsis with a form of the word of the body that you're orbiting. So for example, if you're orbiting around the Earth, we call it perigee for geo. And when you are farthest from the Earth, we call it apogee as opposed to apoapsis. When we're talking about the sun, we use helion. So perihelion is when you're closest to the sun. Aphelion is when you're farthest from the sun. There are at least 3 different words that are used for the moon. There's periselene when you're closest to the moon. There's also perilune, and there's perisyntheon. So because lune, syntheon, and selene are all used for the moon. So it gets a bit confusing there. The farthest point is called aposelene, aposyntheon, or apolune. And then for Mars, the term that's often used is perierion, which is the closest point, and aperion, which is the farthest point. But I think you'll always be correct if you just use periapsis and apoapsis, because then it doesn't refer to any specific body. So the minimum distance from a body. Now, if you want to calculate, so imagine that you know the semi-major axis of your orbit. So you know what the size of the orbit is, but you want to know how close you are here and how far you are here. Well, the periapsis distance, the minimum distance to the body that you're orbiting, the distance at periapsis, is the semi-major axis, which is usually denoted by the letter A, times 1 minus the eccentricity. Okay, so you just take the eccentricity, subtract it from 1, multiply by the semi-major axis, which remember is half the major axis, and that will give you the minimum distance, or the distance from the body at periapsis. The distance at apoapsis is simply the semi-major axis times 1 plus the eccentricity. Okay? Now, this little e that we're talking about here, just to be clear, this little e is the geometric term for the eccentricity of a body. It is not the exponent, the natural exponent that occurs in the natural world. So this is a specific e that refers to the eccentricity of an ellipse. And if you know how close something is at apoapsis, and you know how close it is at periapsis, and how far it is at apoapsis, you can use that to determine the eccentricity. The eccentricity is just the maximum distance minus the minimum distance divided by the maximum distance plus the minimum distance. Now, a thing about all these formulas is to remember, if you need them on the quizzes, I will give you an equation sheet that has all the formulas on there. I don't want you to memorize the formulas. You do have to know how to use them, and we're going to get some practice using them, but just know that you don't have to memorize them, right? You can always look at this sheet that has the formulas on it. All right. Let's put this to use. Let's do some calculations with these. So the average distance from the Earth to the Sun in astronomy, so the distance from the Earth to the Sun is about 93 million miles. It's about 149.7 million kilometers. Or in astronomy, we've defined a new unit of measurement called the astronomical unit, where 1 astronomical unit is the average distance from the Earth to the Sun. So if the distance from the Earth to the Sun is 1 astronomical unit, and the eccentricity of the Earth's orbit is 0.0167, then what's the distance from the Earth to the Sun in astronomical units when the Earth is closest to the Sun in January? And what's the distance from the Earth to the Sun when the Earth is at aphelion in July, when it's farthest from the Sun? And that's right, just to emphasize this, we are closest to the Sun in January and we are farthest from the Sun in July, because the distance to the Sun has nothing at all to do with our seasons. So go out there, do these 2 lecture exercises, calculate in astronomical units how close we are to the Sun in January at perihelion and how far we are from the Sun in July at aphelion. So go out and do that and come back and I'll show you the answer. All right, so what's the answer to this one? Well, the answer to this one is the perihelion distance is the semi-major axis times 1 minus the eccentricity. The semi-major axis of the Earth's orbit is defined to be 1 astronomical unit. So we have 1 astronomical unit times 1 minus the Earth's eccentricity, which is 0.0167. 1 minus 0.0167 is 0.9833. So 1 astronomical unit times 0.9833 is 0.9833 astronomical units. Now, you might be wondering in this case, hey, wait a second, what about significant figures? Isn't Mr. Murphy not obeying significant figures there? Remember that this is a definition. The definition of the Earth's orbit around the sun, or let me phrase it the other way, 1 astronomical unit is defined to be the semi-major axis of the Earth's orbit. So the semi-major axis of the Earth's orbit is precisely 1 astronomical unit. And because it's a defined quantity, it's defined to be 1, I don't have to worry about significant figures in that case. I don't have to worry about significant figures for this one because it's just a constant. So the only place that significant figures play a role here is in the eccentricity, and I gave that to you to 4 decimal places, so the answer comes out to 4 decimal places. So that is when we are closest to the sun. We're 0.9833 astronomical units from the sun. Now, at aphelion, when we are farthest from the sun, at apoapsis, the maximum distance is the semi-major axis times 1 plus e. So that's 1 astronomical unit times 1 plus 0.0167, or 1 times 1.0167, or 1.0167 astronomical units. That's the distance when we are farthest from the sun. Now, just looking at those two, right away you can see that if the average distance from the Earth to the sun is 1, when we are closest to the sun, we're about 1.7% closer than average, and when we're farthest from the sun, we're about 1.7% farther than average. And think about the difference between a really hot summer day and a really cold winter day. And what you'll realize is that the difference between a hot summer day and a cold summer day probably doesn't come down to the fact that the Earth is about 1.7% closer or 1.7% farther. There must be something bigger going on to cause the huge temperature swings that we see here, especially at mid-northern latitudes. And if you take Astronomy 1210, as I said, you'll see that it's actually the tilt of the Earth, the fact that the Earth is tilted over by 23.5 degrees. That's what causes our seasons, not our distance to the sun. Because not only that, if it was the distance to the sun, then we would have summer when we are closest to the sun in January, and we would have winter when we're farthest from the sun in July. And in fact, our seasons are opposite that. But enough on the seasons. Let's do it in miles right now. 1 astronomical unit is 1.496 times 10 to the 8th kilometers. That is 149.6 million kilometers. So what's the distance from the Earth to the sun in kilometers when the Earth is at perihelion? And what is it in kilometers when the Earth is at aphelion? So go ahead and do these calculations. I will pause here. You should pause the lecture here for a few seconds while you go out to the lecture exercise and do these for practice. All right, what did you get on this one? Well, on this one, what you should have gotten is that the perihelion distance is a times 1 minus e. A in this case is 1.496 times 10 to the 8th kilometers. We've already seen 1 minus 0.0167 is 0.9833 times 1.496 times 10 to the 8th kilometers. And there it is, it's 1.471 times 10 to the 8th kilometers. At our farthest from the sun, at apoapsis or aphelion, it's a times 1 plus e, and the answer comes out to be 1.521 times 10 to the 8th kilometers. So those are our respective distances when we are closest to the sun and farthest from the sun. Now, as I said, the Earth's orbit is pretty close to perfectly circular. That's not true of everything in our solar system. Many of the objects, like Halley's Comet, are on highly elliptical orbits. Here's the orbit of Halley's Comet during your lifetime. So it had a close pass to the sun in 1986, and Halley's Comet takes about 73 years to orbit the sun, plus or minus a couple of years, depending on whether it has interactions with Jupiter or any of the other major planets, mostly Jupiter. But it was closest to the sun in 1986. It'll be closest to the sun again in 2061. Right now, in the early 2020s, it's actually coming out here to its aphelion distance. So in fact, in 2024, Halley's Comet will reach aphelion from the sun. It's since 1986 been pulling farther and farther away from the sun. It'll reach aphelion in 2024, and then it will swing in and come close to the sun again in 2061. So hopefully you will see Halley's Comet on its next pass around the sun in the year 2061. Now, there are other kinds of orbits besides elliptical orbits, but these are non-bound orbits. That is, a bound orbit where the object is bound to our sun are elliptical orbits. There are also parabolic orbits and hyperbolic orbits, and these are for objects that are unbound to the sun. This is also what you would get, for example, for a spacecraft that we send to Mars. As that spacecraft comes into Mars, it's traveling so fast that, in fact, the gravity of Mars will bend it, but it's traveling so fast that it will escape from Mars, and it's on an unbound hyperbolic orbit. In the history of humanity, we've only discovered two objects on clearly hyperbolic orbits that were not part of our solar system, that traveled through our solar system. And those two objects were actually discovered just in the past four or 5 years. The first one was discovered in October of 2017, and it was discovered by an observatory in Hawaii. So they used the Hawaiian word Oumuamua to describe, to name this object. And Oumuamua, there's various translations. It means scout or visitor from very far away. But the eccentricity of its orbit was 1.19951. Because it's larger than 1, its orbit is hyperbolic. And because it's a hyperbolic orbit, this object is not an object that's in permanent orbit around our sun. This was an object from interstellar space that came through our solar system. Our sun bent its orbit and it went back out again. In fact, here's what the orbit of Oumuamua looks like. It came in almost perpendicular to the plane of our solar system. The sun's gravity bent its orbit, and Oumuamua left the solar system on a hyperbolic orbit there. Based on our observations of the object, it was much too small to resolve. We couldn't take, other than seeing it as a little tiny point of light, even through the biggest telescopes, it looked like a little tiny point of light. But based on its brightness, we estimate that it was somewhere between about 100 and 1,000 meters long, and then it was about 30 to 170 meters thick. So we think that this was a long, flattish shaped object. There has been some wild speculation that Oumuamua may in fact be an interstellar visitor, possibly a vehicle built by an extraterrestrial intelligence that was flying through our solar system. And I think that's highly unlikely. I think that there are many, many natural explanations that are much more likely than an interstellar visitor. But in any case, that's Oumuamua. There's a picture of it as to what it looked like through the best ground-based telescopes. It really looked just like a little dot of light. It was much too small to see more than that. Interestingly, just 2 years after Oumuamua, in August of 2019, we discovered the second one of these, and this was the comet Borisov, named for the astronomer who first discovered the comet. It was the second extrasolar object discovered. The eccentricity of its orbit is 3.357, so it's on a highly eccentric orbit. And this is clearly a comet. It was about 0.5 kilometer in size. And here's a picture of the orbits of Oumuamua and Borisov at the same time as they flew through the solar system. The two objects are unrelated to one another. You can see that they came in on very different trajectories, and they certainly left on very different trajectories. But those are the two extraterrestrial objects we've discovered so far. And then here's a picture of Comet Borisov made with the Hubble Space Telescope, Wide Field Camera 3. And you can see the bright nucleus of where you can see the nucleus of the comet right there. The actual comet itself, the little icy dirt ball or the dirty ice ball that makes up the comet, and by that I mean it's made of mostly water ice and dirt, is about 0.5 kilometer across. It would be a tiny little point of light down at the center of that nucleus. We can't even see that object itself. What we're seeing here is dust and gas that have been shed by the comet. All right, enough on Kepler's first law. Let's talk about Kepler's second law of planetary motion. Kepler's second law states, and I'll tell you how to state this a little more clearly in a minute, but it states that the straight line joining a planet and the sun sweeps out equal areas in space in equal intervals of time. So what does he mean by that? What Kepler meant is that if you take a planet orbiting the sun, or in this case, because it's such an elliptical orbit, and none of the planets are on an orbit this elliptical, let's call it a comet or an asteroid. If you have a comet orbiting the sun like this, and we draw a line between the planet and the sun, and we let 1 year go by, say in Halley's Comet, and we measure the area that it sweeps out in that 1 year. And then when it's far from the sun, we also let 1 year go by, and we measure the area of this triangle the area of this triangle is the same as the area of this triangle. That is, this line sweeps out equal areas in equal times. So the area of this triangle is equal to the area of that triangle. Now, let's take a look at that. So here's an example of that. So each one of these periods of time is the same, and the areas of all these triangles are the same. So why did Kepler say this? I mean, it's a crazy thing to say. What's important about this? There's another way to phrase Kepler's second law, and Kepler's second law can be phrased like this. When an object is closest to the sun, it moves fastest, and when an object is farthest from the sun, it moves slowest. Because see, look, when the object is close to the sun, this triangle is not very tall, so it has to be very wide. And to be very wide, that means, because remember, distance is speed times time, to be very wide, the comet has to be moving very fast. But out here, the triangle is very tall but very skinny. The planet does not move very much in 1 year. So you'll notice if you look at the distance that the planet moved in 1 year here, it's less than the comet. The distance that the comet moved in 1 year here is less than the distance that the comet moved in 1 year there. So another way to phrase Kepler's second law of planetary motion is that when objects are close to the sun, they move faster, and when objects are farther from the sun, they move slower. And you can see that in this little diagram. Notice how this object slows down as it gets far from the sun, and then it speeds up as it gets close to the sun. A little animation of Halley's Comet really shows this. Watch as Halley's Comet whips around the sun and then comes back out. Halley's Comet spends the vast majority of its time out here at the farthest reaches of the solar system. It spends hardly any time in the inner solar system. Hopefully you noticed that when I showed you this diagram before. Look at what Halley's Comet did from 1986 to 1987. In 1 year, it traveled almost all the way out to the orbit of Jupiter. And in just 3 years, it was all the way out at the orbit of Saturn. But then it took it 6 years to get out to Uranus, and it took it over 10 years after that to get out to the orbit of Neptune. But from 2005 until about 2040, it spends those 35 years hardly moving in the outer solar system at all. And each one of these little tick marks is a year right here. Look at how slowly it's moving here. Orbits, when bodies are orbiting the sun, they spend their vast majority of their time, especially on highly elliptical orbits like this, they move much faster when they're closer to the sun, much slower when they're further from the sun, and they spend most of their time out here. You'll notice here, in 2060 to 2061 to 2062, Halley's Comet in just a 1 year period is going to whip around the sun. So you don't have much time to see it. You only have a couple months when it is closest to the sun and closest to Earth to see it very well before it starts rapidly pulling out of the solar system. So you might say to yourself, well, why didn't Kepler just say that? I mean, why did Kepler have this straight line joining a planet and the sun sweeps out equal areas of space in equal intervals of time? Why did he say that and not just say it moves faster when it's closest to the sun and slower when it's farther from the sun? And the reason Kepler phrased it like this was he wanted to know what the mathematical relationship is between the speed here and the speed here. That is, Kepler could measure the area of this triangle and he could measure the area of that triangle, and he wanted to find out how much faster the planet is moving here and how much slower. The way I phrased it, planets move faster here and slower out here, doesn't really tell you how much faster or how much slower. But Kepler's does, because if the area of this is equal to the area of that, and you know the height of this triangle, that is the distance from the comet to the sun here, and you know the size, the height of this triangle, the distance from the comet to the sun here, if you know the heights of these, you can figure out how big the bases have to be so that the two have the same area, and that tells you how fast the comet is traveling. That's why Kepler did this. That's why he expressed the law that way, in equal areas of an equal time. But there's something deeper behind it. Because in Kepler's second law, the area of the triangle is conserved. It doesn't change. And in physics, conservation laws are really important. When we have things that are conserved, on the face of it, it sounds simple, right? You probably remember from high school chemistry class that mass is conserved in a chemical reaction. But that means that there's a much deeper underlying chemistry or underlying physics in that case. It means that, even if you react something and the mass of the product is less than the mass of the reactants that went in, then some of the product must have been given off in a form that you couldn't measure. The same thing is true in physics. these laws, these conservation laws, give us a really deep probe into the underlying physics. So if something is being conserved here, it's actually worth spending a minute talking about what's being conserved. Well, what's being conserved, according to Kepler, is the area of the triangle. What does the area represent? Well, think about a triangle. The area of a triangle is 1/2 times the height times the base. So let's think about the orbit of this comet. So here's the sun. The comet is on this highly elliptical orbit around the sun. So here's just a moment in time. We've got the distance here from the comet to the sun, and we've got the base. And the area is just 1/2 times the height, which is r, times the base. Well, how wide is the base? The base, remember, distance is just speed times time. So it's the velocity of the object times the length of time. So the area is 1/2 VTR. So that is the quantity that is conserved. The velocity times the time times the distance to the sun. Now, Kepler already told us that he was doing it for equal intervals of time. So we don't have to worry about the time here. We know that's equal because Kepler said it to be equal. What Kepler really realized was that the velocity and the r are a constant. And that is, if you are twice as close, you must be traveling twice as fast, so that the two quantities are conserved. If r is half as big, then v must be twice as large, so that these two quantities will produce the same area. Today, we understand this as angular momentum. The angular momentum of a spinning object, so if you think of an ice skater spinning, the angular momentum is the mass of the object times the speed at which it's moving times the distance from the center. It's mvr. And one of the conservation laws in physics is that angular momentum is conserved. If you change any one of these, you have to change the others in a closed system when angular momentum is conserved. So in the case of planets, if you pull closer to the sun, you have to orbit faster, because in the case of a planet, the mass of the planet's not changing. Let me do an example of this that might make it more clear. Probably the most famous example of the conservation of angular momentum comes from an ice skater spinning. Right? When an ice skater has her arms out, she's spinning very, very slowly. And as she pulls her arms in, she spins much faster. So let's go out to YouTube. Let's find a couple videos of ice skaters spinning here. Now watch what happens. She starts her spin with her arms out, and she's spinning slowly. And as she pulls her arms in, she spins faster and faster and faster. And by the way, that was an ice skater breaking the world record for spinning. That was 308 revolutions per minute she was doing at her fastest. So that's an example of the conservation of angular momentum. As she pulls her arms in, what's happening is r is decreasing. She's pulling her arms in, and therefore the angular speed, she has to speed up. Here's another example of this.
Mastering the backwards prep, you're going to finally try to go forwards. So as you finish the torque, your left arm and left leg are going to go forward, and you're going to try to spin. Ideally, you should try to stay under the toe pick when spinning. Spinning in the middle of your blade.
So watch again that as she goes into the spin, her arms and even her leg are out, and as she brings her arms and leg in, she's reducing her size, she's bringing that mass in, so in order to do that, she has to spin faster from conservation of angular momentum.
You can bring it a bit down as you get faster and faster. Your arms are going simultaneously in as well, and you want to do this all in a very gradual, slow motion.
Okay. So that is a spin, an ice skater spin. So how do we do it in conservation of angular momentum? Well, the angular momentum, that L, is the product of mass times velocity times radius. So as she brings her arms in and reduces her radius, her angular speed, her rotational velocity has to speed up to compensate. So that is Kepler's second law. What this means is that in orbital motion, as the Earth orbits the sun, when we are closest to the sun, we're moving faster than when we are farthest from the sun. When Halley's Comet is closest to the sun, it's moving fastest, and when it's farthest, it's moving slowest. So that is Kepler's second law. Now, Kepler's third law describes the relationship between the orbital period of a planet and how far the planet is from the sun. So the orbital period is how long it takes to orbit the sun, and the semi-major axis is the distance to the sun. And Kepler phrased it this way, that the squares of the planet's periods of revolution are in direct proportion to the cubes of the semi-major axes of their orbits. This is how he described it in words. This is where equations actually make things much simpler. Because what Kepler was really saying is that the distance cubed, the average size of the orbit, the semi-major axis of the orbit cubed, is equal to the period squared. As I said, we usually represent the semi-major axis using the letter A. So A cubed is equal to the period squared. And this holds true if you use special units. This holds true if the distance A is measured in astronomical units and the period P is measured in years. So let's do an example of this. Let's do the Earth as an example. The semi-major axis of the Earth's orbit is 1 astronomical unit, and its period is 1 year. So you can easily see that if we plug 1 cubed, 1 times 1 times 1 is 1. The period squared is 1 year, which is 1 times 1. So 1 cubed is equal to 1 squared is sort of trivial. It all works out. Not very impressive because it was all ones. But let's use a different planet. What is the distance? Let's do Kepler's third law for Jupiter. What is Jupiter's distance from the sun if its period is 11.86 years? Right? So astronomers don't usually use Kepler's law like this, where we know the semi-major axis and the period, and we compute the cube of the semi-major axis and the square of the period and compare them and say, oh, hey, they're the same. Usually what we do is we can determine one, and we use that to determine the other. So for example, what's the distance of Jupiter from the sun if its period is 11.86 years? If you watch Jupiter, you will see that it goes all the way around our sky and comes back in about 12 years. And that's the length of time that it takes Jupiter to orbit the sun, 11.86 years. If it takes 11.86 years to orbit the sun, what's its semi-major axis? How far is it from the sun? Well, let's use Kepler's law. The semi-major axis cubed is the period squared. The period is 11.86 years. It's already expressed in years, so I don't have to do anything about it. So 11.86 squared is 140.7. So the semi-major axis is the cube root of that. So it's actually 140.66. We take the cube root of that, we get 5.20. So Jupiter is 5.20 astronomical units from the sun. That's how far Jupiter is from the sun. If you don't know how to do it, stop now and go out and learn how to take the cube root on your calculator, because you will need it for the quiz and you will need it for the lecture exercise. You need to figure out how to take the cube root of something. Let's do another example of this. Halley's Comet takes 76 years to orbit the sun. What's its average distance from the sun? So the average distance, the distance cubed, is equal to the period squared. So the semi-major axis cubed is 76 squared, right? It takes 76 years to orbit the sun, so it's 76 squared. The semi-major axis cubed is 5,776. So the semi-major axis is the cube root of 5,776. And if you plug that into your calculator, you'll find out that the semi-major axis is 17.9 astronomical units. Now that's half the major axis. So if we go back to the picture of Halley's Comet here, let me go back to that orbital picture of Halley's Comet, that means the semi-major axis is 17.9 astronomical units. The full major axis from one side of the ellipse to the other is double that. It's 36 astronomical units, almost 36 astronomical units from side to side. So when Halley's Comet is closest to the sun, it's actually less than 1 astronomical unit from the sun, and when it's farthest from the sun, it's about 35 astronomical units from the sun, which puts it out beyond the orbit of Neptune there, almost but not quite out to the orbit of Pluto. All right, so that is that. So Kepler's third law allows you to determine the semi-major axis of the orbit if you know the period, or the period if you know the semi-major axis. So let's do this for Mars. The semi-major axis of Mars' orbit is 1.524 astronomical units. How long does it take Mars to orbit the sun, and express your answer in days? So go ahead, take a minute, go out there and do that. How long does it take Mars to orbit the sun, and then express your answer in days? All right, let's see what the answer to this one is. Let's work this one out together just to get a little practice with it. So the semi-major axis of Mars' orbit is 1.524 astronomical units. Now, we need to cube that number. So how are we going to cube that number? I'm using just the scientific calculator. Well, the easiest way to do it, not the easiest way, one way to do it is just the number cubed is 1.524 times 1.524 times 1.524. And so there it is cubed, 3.5396. All right. The other way we can do it on our calculator is you may on your calculator have an x cubed, or in this case, an x raised up to the y right there. And so in this case, we can, let me clear this out here for a second. So we can put in 1.524, and then we can do x to the y, raise it to the third, and we see there it is, raised up to the third power, right? So what I did was I clicked on the Microsoft calculator. And by the way, the Microsoft calculator, there's the standard and the scientific. You're definitely going to want to be on the scientific for this, all right? So that is the semi-major axis cubed. Well, the period is just the square root of that, right? The semi-major axis cubed is the period squared. This is the period squared. So let's take the square root of that, and the square root of that is 1.88 years. So Mars takes 1.88 years to go around the sun. I wanted your answer in days, so let's multiply by 365 and a quarter days in a year. Don't forget that quarter day. It's really important to astronomers. And so the total length it takes Mars to orbit the sun is 687.2 days. And that's to the proper number of significant figures, because I gave you in the problem to begin with that the orbit has 4 significant figures. So the answer is 687.2 days. That's how long it takes Mars to orbit the sun. Okay? All right. Here's the properties of the planets. It is Kepler's third law that determines how this period depends on the average distance of the planet from the sun. And the pattern that you'll notice here is that the further you are from the sun, the longer it takes to orbit the sun, right? The Earth takes 1 year to orbit the sun. Mars, which is about 1.5 times further from the sun than we are, takes 1.8 years. Jupiter, at 5.2 astronomical units, takes a little less than 12 years to orbit the sun. Saturn, at a little bit less than 10 astronomical units, takes almost 30 years to orbit the sun. Uranus takes about 84 years to orbit the sun, Neptune about 165, and then Pluto down there at the very bottom. It's almost 40 times further from the sun than we are. 39.44 astronomical units, takes 248.6 years to orbit the sun. So that is Pluto's orbital period. All right, let's talk about where this comes from. Kepler was an interesting character. Kepler not only derived Kepler's third law, that the semi-major axis cubed is the period squared, but Kepler wanted to understand where it came from. So Kepler was trying to understand why the semi-major axis cubed is the period squared. Now, Kepler was a bit mystical, and he thought it might have to do with geometric figures. He even thought it might have to do with musical notes, and he investigated all kinds of things, and he never came up with an answer. Kepler passes away, and of course it was Isaac Newton that picked up this problem, and Isaac Newton figured out the answer. And that's because Isaac Newton understood that what holds something in orbit, right, there's a force holding it. If its velocity is constantly changing because it's moving in a circle, there must be a force acting on the body. In the case of a planet orbiting the sun, that force is provided by gravity. But he also knew what the centripetal acceleration was, what the centripetal force was. He could just calculate that using some geometry. And what Newton figured is that the centripetal force, the force pulling towards the center, is the result of gravity. So the centripetal force must be the same thing as the force of gravity. Well, the centripetal force is mv squared over r. M is the mass of the body, v is how fast it's moving, and r is the distance from the center out to the body. And that has to be equal to the force of gravity acting on the body. G times the mass of the body it's orbiting times the mass of the small body divided by the distance squared. And you'll notice that the small m is on both sides of the equations, and so it cancels out. So the orbital velocity squared is gm over r, and so the orbital velocity is the square root of gm over r. We derived this in the last lecture. But now let's take it a little step further. How do we get Kepler's law out of this? Well, to derive Kepler's third law, we do the same thing. mv squared over r is gmm over r squared. The circular orbit velocity squared is gm over r. But now we remember that the velocity, the speed of an object, is the distance that it covers divided by the time that it takes to cover that distance. Distance, or speed, is distance divided by time. Well, the distance that the body covers is 2 pi times the radius. That is, the circumference of this circle is 2 pi times the radius of the circle. And the length of time it takes it to do it is the period of the orbit. So the velocity is 2 pi times the radius of the orbit divided by the period of the orbit. And so if we plug that in here for v squared, we get that 2 pi r over the period squared is equal to gm over r. And then with a little bit of algebra, right, we've got an r squared over here. We've got a 4 pi squared r squared over the period squared and a gm over r here. If we multiply both sides by r to get rid of that r, and then multiply both sides by p squared to get rid of that p squared, we get 4 pi squared r cubed is equal to gm times the period squared. So the semi-major axis cubed is gm over 4 pi squared times the period squared. Or to invert that equation, the period squared is 4 pi squared r cubed over gm. This is Newton's version of Kepler's third law. And what's important about this one is, in this case, because we're using g in here, the mass has to be measured in kilograms, and the distance, the semi-major axis, has to be put into this equation in meters, right? Because those are the units for our g. So that first simple version that Kepler discovered, the distance was in astronomical units in the period in years, but because Newton was using kilograms and meters, or I shouldn't say that, but because today we're using kilograms and meters, now we have to use Newton's form of the law, 4 pi squared r cubed over gm, or in the case of finding the semi-major axis cubed, gm over 4 pi squared times the period squared. Okay, so that's that. And just remember that r in this case is the orbital radius from, if we're talking about satellites going around the Earth, from the center of the Earth. If we're talking about planets going around the sun, it's from the center of the sun. And that's just the semi-major axis. So the r here, we can substitute in a for r because they both mean the same thing. So let's do this. Let's do an example with this. So here's a lecture exercise. What is the period of the orbit of the International Space Station if it's 420 kilometers above the Earth? And I want you to express your answer in minutes, right? So use Kepler's law as you just saw it, Newton's version of Kepler's law. You've got this semi-major axis there. Well, actually, you don't. What you have is the height of the International Space Station above the surface of the Earth. You'll need to remember that the radius of the Earth, you don't have to memorize it. If you need it on a quiz, I'll give it to you. I should have given it to you in this problem. Sorry, I forgot. Remember that the radius of the Earth is 6,378 kilometers. So you'll have to add the 420 onto the 6,378 to get the semi-major axis of the space station's orbit, and use that to calculate its period. How long does it take the space station to go around the Earth? All right, let's work it out. Let's see what we get. The period squared is 4 pi squared r cubed over gm. So now it's just plugging the numbers in, being really careful with our math here because there's a lot of scientific notation. There's a cube in here. Can't forget that cube. So 4 pi squared times the distance r, the semi-major axis of the orbit. Well, that is 6,378, which is the radius of the Earth, plus 420, which is 6.798 times 10 to the 6th meters. Remember, it has to be in meters, so you have to convert your kilometers into meters, and don't forget to cube that. Divided by g, 6.674 times 10 to the minus 11th, divided by the mass of the Earth, which is 5.972 times 10 to the 24 kilograms. Plugging all that into our calculator, we get that the period squared is 3.112 times 10 to the 7th seconds squared. Don't forget to take the square root, right? Because this is the period squared. So the period is the square root of that, which is 5,578 seconds or 93 minutes. So it takes the space station 93 minutes to go around the Earth. All right. So that's how we use Newton's modification to find Kepler's third law. The last thing I'm going to mention about Kepler's third law is something that really applies mostly in astronomy, not spaceflight, but I just want to be technically correct about it, that when we think of a satellite orbiting the Earth, we think of the Earth sitting still with the satellite orbiting it, but that's not always true in astronomy. For example, when we have a binary star system and we have two stars orbiting around one another, it's not true that one star is sitting still with the other orbiting it. Both stars are orbiting one another. And in fact, both stars are orbiting a point in the middle that's called the center of mass of the system. So one star doesn't orbit the other. They're both orbiting one another. And in fact, they're both orbiting the center of mass of the system. So how do you determine where the center of mass of the system is? Well, to do that, you imagine a giant seesaw. And the seesaw, the center of mass, is where you would put the fulcrum of the seesaw to balance the two out, right? You're probably familiar with seesaws from when you were a kid, that if we had a small child and a large child, and they were both the same distance from the center, that is, if the small child was on the edge and the large child was on the edge, then the seesaw wouldn't balance. The large child would be down. But if we move the large child closer to the center, we can find a point where the two of them balance. And the point that they balance on there is called the center of mass. So the center of mass in a stellar system, you just pretend that you've got a giant seesaw. You put one low mass star on the seesaw, the high mass star on the seesaw, and the center of mass is simply where the two of those would balance one another out. And the two stars are orbiting that center of mass. And so here's another example with a binary star system of two stars orbiting one another. They orbit the center of mass there. Nobody's sitting still. So to be technical about Newton's modification to Kepler's third law, this is what it should actually look like. It should be that the period squared is 4 pi squared r cubed over g times the mass of the two bodies added together. And that would be, in the case of the Earth orbiting the Sun, the mass of the Sun plus the mass of the Earth. Or in the case of a comet orbiting the Sun, the mass of the Sun plus the mass of the comet. But here's why we don't usually add the two masses together. Because in astronomy, typically, the Sun is much, much bigger than any of the planets, right? It's more than 1,000 times more massive than all the planets put together. So with the Sun being that massive, it turns out when you take a really big number and add a small number to it, it just ends up being the really big number, right? If you think about the deficit of the United States, the trillions of dollars of the deficit of the United States, annual deficit, and then you add a couple dollars to it, well, the deficit is still trillions of dollars. When you have a really big number, you add a little bit to it, it's still a really big number. So typically in astronomy, we ignore the fact that it's M1 plus M2. In the case of satellites orbiting the Earth, we can feel free to ignore this as well, right? If you think about a satellite orbiting the Earth, the mass of the Earth is enormous. The mass of the satellite is minuscule compared to the mass of the Earth. So the mass of the Earth plus the mass of the satellite, it's still just the mass of the Earth. I mean, if you were going to carry it out to 20 significant figures, then you might have to worry about it. But if you're just going to do it to 3 or 4 or 5 significant, or 5 or 7 or 8 or 9 or 10 significant figures, it's not going to matter at all. It's just going to be the mass of the Earth. So that's why we use the simple version and we don't have to use this M1 plus M2. So this ends the first part of lecture 4. So we've talked about Kepler's laws of planetary motion. And what we've seen is that all orbits are elliptical, with the Sun at one center, or in the case of orbits, I should have mentioned this, let me mention it now, that in the cases of objects orbiting the Earth sits at one focus and the other focus is empty. There's nothing there. Right? The second thing is that angular momentum is conserved. As a satellite orbits close to the Earth, it moves faster. As it pulls farther from the Earth, it moves slower. And then it moves, and then we saw with the angular momentum there that it moves faster in proportion to its distance from the Earth. And then with Kepler's third law, we saw that the semi-major axis cubed and the period squared of the orbit are related to one another. In the next lecture, we're actually going to talk about orbits themselves. We're going to start by talking about what parameters do we use to define the shape and the orientation of an orbit and the location of a satellite in that orbit. And then we will talk about the different kinds of orbits that are used for satellites orbiting the Earth, and we'll talk a little bit about their uses. So join me in Lecture 4 Orbits, Part 2, when we talk about orbital parameters and the shapes and uses of orbits.